Okay, so like I mentioned, that quiz that we just did, it can only help your grade. If you did worse than the first quiz, then I won't replace the grade. If you did better, then I will. Um, you've just turned in homework 7, and the next one isn't available on Blackboard yet. I have to put it up after class, but it's just a very, very simple activity for you to do in WMS to reinforce what we're going to be going over in class today and then also in class on Monday. So my my mindset on homework assignments during the watershed modeling part of the course is to break it up into really simple basic steps where you're only in one homework assignment kind of demonstrating your proficiency in a single skill. So the first skill that we're going to be going over today and on Monday is how to obtain watershed data and how to delineate a watershed. And then future assignments will be adding a new model on top of those. So it'll be like using the rational method to calculate runoff, using TR55 to calculate runoff, and so on. So the first one, even though the assignment's a pretty quick turnaround for homework number 8, I don't think that you'll find it too taxing because I deliberately make these watershed modeling homework problems pretty light. So today we're going to go over how you get data, how you get aerial photos and other images loaded in the background, and then how to delineate a watershed. So start WMS, and we did kind of a brief tour of the program last time where we left off was like the step of defining the coordinate system that you were using and then also setting the project area. So let's start from scratch but do those same steps. And this next time, I don't think that we're going to have to define the projection or the coordinate system. So if you start with the hydrologic modeling wizard, we're going to focus on Ritter Park in Huntington. And there's a stream that goes through Ritter Park, Four-Pole Creek, that's kind of notorious for flooding. So we're going to look at that a couple of times this semester, and today will be our first taste of that. So click on the icon for the hydrologic modeling wizard. And we're going to create a new file name, so browse to a location that you're going to be able to come back to. For me, I've created a WMS files folder just in the C drive. So C, WMS files, and I'll call this one 3-1-24 for today's date. All right, so this is Four-Pole Creek. So once you establish the file name, then you have to click on the save icon before up here it will reflect the new file name that you've saved for the project. So right now it says untitled and it's not saved anywhere, but when you click on save, now if the program has to restart, then we don't have to begin from scratch. And once in a while, the things that we have the program do are pretty computationally intensive and it can crash the program. So it's a good habit to save occasionally. Unfortunately, it doesn't auto-save. It's not like when you're working on a Word document or Excel, and if you've saved it in OneDrive, sometimes it'll automatically save for you. Here it won't do that. You have to manually click save. So once you've established the file name, then click on next, and what you should have already from previously was the projection defined. And if not, if you didn't have your computer on Wednesday and you didn't already define the projection, the way to do that is click on define, and it probably starts off as no projection, but switch it to global, and then selecting set projection, then we're going to scroll down through the projected coordinate systems. Scroll down, and you'll find what we want to do under UTM, and it can be either under NAD 1983 or, well, no, we'll do it under NAD 1983, and then West Virginia is contained within Zone 17. There's different, depending on the longitude of your location is what determines which UTM zone to use. So NAD 83, UTM zone 17, so click OK, and then the vertical datum, excuse me, NAVD 88 and meters. All right. So this is kind of where we left off before. This coordinate values, there's 4 of them. What you're going to be defining is the edge of your project area. So there's 4 corners in a rectangle, and it needs to know the coordinates for each of them, like an x, y, for all 4 of those corners. So the far western edge value, the far northern edge value, and so on. So if you click define, then it brings up this virtual Earth map locator tool. You can see right now it just goes to the previous location that you were on. And I had brought it up on Charlotte, North Carolina previously. In our case, we want Huntington. So you can either like zoom out and then just pan your way to Huntington, or you can type Huntington into here and jump. All right, so let me show you a representation of where we're going to be working today. Here's Ritter Park. This is Hal Greer as it's coming into town. So if you know where the hospital is on the right side, the Frost Stop on the left side. So this Washington Boulevard, if you turn left there, there's a creek that runs alongside the road. So Washington turns into Enslow Boulevard. And so this 4-pole creek is kind of notorious because it causes flooding down here in this neighborhood. It's a real problem for the homes there, like completely immersing some of the homes in this neighborhood. Causes flooding in the vicinity of Ritter Park. In fact, there's pictures of Washington Avenue like completely submerged because of flooding of 4-pole creek. So what we're going to do is we want to know in the vicinity of this shelter, Ritter Park shelter. So if you've ever been to like a picnic at Ritter Park, or been walking around and seen people having a cookout there, there's a creek that goes right by that pavilion. And we're going to find out for that location how much area is upstream, how much watershed area is contributing to the flow at that location. Like, is it a 10-acre watershed that's contributing to flow into the creek there? 10 square miles? What's the area of the watershed at that location? So that's what we're interested in. So here, when it's showing you a location, it's only going to download elevation data for what's in the window. And the more zoomed out you are, you've got more elevation data it's going to download. So if you zoom out really far, it's going to take a long time to download all of the data. I mean, most likely you'll have your whole data set downloaded, but it's going to take a long time, and it's going to be downsampled. Like the precision or the resolution of the data set is worse if you're zooming out. It's not going to get all the pixels, so to speak, of the data. So there's an advantage to only downloading the area that you need. And this is sometimes an iterative process, because sometimes you'll think, well, for example, if I said this, if I thought, here's Ritter Park, so I want to have all of the streams that contribute to flow up to that point. So if we follow the stream backwards, here is that 4-pole creek, and if it goes off the screen, like if you can still see the creek and it goes off the screen, then you don't have all of the contributing area yet. So we need to zoom out a little bit more. Now maybe we have all of the contributing area, but we're never exactly sure until we go through the delineation process. So there will be a couple of times where, this semester you will think, okay, this has got to be my right project area. Then you'll go through a few more steps and you'll delineate, and then you'll just have a horizontal flat line at the bottom. And that'll tell you, no, you didn't go get all of your data. So I don't know if that'll happen today, but we will see it eventually, and I'll point it out when we do. But make it so that your screen looks about like this. Let's use this as our approximate extents. And once you select OK, what it's going to do is it's going to put values into these 4 coordinate positions. So we've defined the far western edge, the far northern, south, east. So we've defined the coordinates. Anybody have questions so far? Okay, so click Next. And you're going to have to tick the box that says Use Web Services. And this is one of the one of the greatest value added that WMS brings to the table is so that you don't have to manually obtain all of your data. They'll go get it for you, and only for the area that you're interested in. So you could go and get all of the data from government websites yourself and load them in manually, but this web service will save you potentially hours of trouble. So check that box and then click Next. Now, this window is asking which data do you want WMS to go and get. And there's a lot of different data types it can go and get. The ones that we'll mostly use are worldwide elevation data. So turn that on, worldwide elevation data. Oftentimes it would be good to go get NLCD. That stands for National Land Cover Database. I don't want it today, so I'm going to turn it off. So I'm also going to turn off SURGO, and you've heard of that before when we talked about soil data. There's StatsGo and SURGO. So it will go and get land cover details. It'll go and get soil type details, which that's really valuable to have when you're calculating the curve number. But today we're only going to be delineating the watershed, so we don't need either of those. We just want worldwide elevation data. Now, in parentheses, it says variable resolution. What that means is some places in the United States, there's really good elevation data available. Like they've flown LiDAR. If you've heard of LiDAR before, it's like an aerial tool that can measure the ground surface to like millimeter accuracy. And then there's other places like really remote areas of Alaska where they don't have the same level of precision. And then there are locations outside the United States that have even worse data than that, and sometimes no data. So what it'll do is it'll find the best data it can, but the more zoomed in you are, the higher resolution the data will be, and it gives you the option of how downsampled you want the data to be. It'll suggest something, and you can override it. So if you've got the worldwide elevation data selected, now click on the button below it. We're not going to go next. We're going to download data from web. And it's just popped up this question. So zoom level 12, resolution of 30 meters. That means for this area that we're working on, it's going to go and find an elevation point every 30 meters. And so think about, it's kind of like the pixels of a picture. It's going to tell you how closely spaced are those pixels. So they're 30 meters away for each elevation measurement. Obviously, the lower that is, 15 meters, means that you have higher resolution data, but then it takes longer to download, and your computer is more prone to crashing when you run computation on really high resolution data. So like how high of a resolution you need partly depends on whether you've got steep watersheds or flat watersheds. In West Virginia, we have really steep watersheds with lots of relief. And so a 30-meter resolution is plenty of detail for us, especially with the big scale that we're working at. So it'll give you a suggested default, and almost always the suggested default is fine. So just click OK, and it'll take a moment to go and download that data. At the bottom of the screen, in red, it will give you some sort of like a little message as it's downloading and loading it. But then you know that it did its thing when all of a sudden a bunch of colors appear in the background. So let's close the wizard for a moment and just look at what we've got. So we've got this picture, and remember what the area looks like. Let me zoom out a little bit. Do you see any sort of similarities? So here's Huntington. This is the flat part of Huntington. And so there's definitely some shape similarities. And if we're still not sure what we're looking at, we can bring in aerial photos on top of it. So there's Get Online Maps. So if you hover over this cursor here, it looks like maybe 4 little faint tiles. Get Online Maps. It'll offer you some possibilities. You can either get an aerial photo or a street map. or a topographic map. I find the street maps to be pretty helpful. Let me load the street map. So I click OK, and what it does is now on the left side of the screen, it's added another layer of data. It's going to get the worldwide street map. And so now those contour lines that it generated by downloading the elevation data are drawn on top of this street map. So I'm interested, I can zoom in on the park area. I'm interested over here in the park. And we wait a moment and it will kind of clean up the resolution of that. So here's the creek as it goes by the park. Zoom out a little, it'll get the image. It's a little bit slow. Okay, so we've got this, this data, and now I'm going to zoom to the extents. Just keep zooming out here. What I want it to do is I want it to predict where streams are going to be forming. Let me turn off, by the way, the background image. So if you just check that box where it says GIS data, it's still there if I want to bring it back. Like I can turn it back on again, but I don't want to see it at the moment. I just want to see only these contour lines. So bring up the hydrologic modeling wizard again. And so let's skip. Oh, by the way, maybe now would be a good time for us to save our work. So click on save in case things crash. It's always good to save occasionally. Okay, so in the wizard, let's skip through. We've already defined the projection. Skip through the web services. Don't click download data again, because if you do, if you click that another time, it's going to go download everything and then create duplicates. So just skip past that. All right, so we're on this compute flow directions and accumulation. So we're on a step that's called topaz. Compute topaz. Topaz is a little algorithm that what it does is it looks at the elevation for every cell in the watershed, and it asks the question, what's the elevation of all of the adjacent cells? And so what it's looking for is if it rains on this pixel, what direction is the water going to flow from that pixel? And what it does is it finds the cell that's the lowest of all the adjacent cells, and then it points an arrow at the lowest cell. So it does this big global comparison of all of the pixels, and it finds out what is the direction of flow if the rain falls in any location. What's the route it would take to get towards the outlet? So down here, this setting, minimum flow accumulation threshold, by computing topaz, what we're going to do is it's going to give us an estimate of where streams would form. It's going to find the lowest points in the watershed that have upstream contributing area, and then it's going to put a blue line there. So change it to 10 acres. It's as good as anything. And you might have different units. It may be started off as square miles. You can choose which units you want for the sub-basin area. I have it as 10 acres, and then click topaz. It'll take a moment or two to calculate it, and when it's done, this little pop-up window should say normal program termination. So OK. And then what it does is now there's all these extra blue lines that look a lot like where the creek would be. And that's what it is. It's predicting where streams will form because those are low-lying areas that have flow being contributed from other directions. So this is a very useful and important step. And the good news is it looks like we're going to have all of the area that contributes to Four Pole Creek. Like this is the stream. This is Four Pole Creek here. It's got a couple of different legs, but you see that you're going to get used to looking at things like this, but there's all of these branches that are going down. So like the boundaries of the watershed, draw a line that doesn't intersect any of those, and that's going to be the watershed boundaries. You'll get good at kind of seeing the outline of it over time, but we've computed topaz, and if you click next, the final step in delineation is to create an outlet point. So we have to drop a pin in the location that we're interested in. And remember, I said it is by that pavilion. So it's this Ritter Park shelter. So we're going to have to look for where does the creek, it's going north, and then suddenly it goes west. That'll help us to find the location. Well, also we can turn the imagery on. So let's zoom in over here and turn on the imagery again. Yeah, here's Harvey Town. Let me scroll to the side. Oh, yeah. Ritter Park. Okay, so we're going to drop a pin at the location of the pavilion. And there's all these little branches coming in. So this branch is a small one compared to the main branch here. But we want to be just downstream where the two come together. So click on Create Outlet Point, and this part is very important. If you click in the wrong spot, it's a nuisance to delete them. There is this tool for Delete Outlet Point, but this is kind of like a high-stakes step of clicking in the right location. So don't click in the wrong location. Just get it right in the middle of that blue line and drop the pin. Okay, so once you do that, click Next and Delineate Watershed. It's going to do some calculations. When I click it, watch what it's saying down at the bottom in red. It's going to give us a little countdown or kind of a report on its estimations related to watershed delineation. Okay, so it's telling us that the contributing area is 7945 acres. So how many acres are there in a square mile? Does anybody know that? 640. So 7945 divided by 640. So that's about 12 square miles. But we've got a problem. Do you remember I told you about that horizontal line? We don't have all of the watershed. Probably the watershed goes just like a little bit further. So there's a little bit of the watershed that's been cut off at the bottom there. So what would we have to do? Throw everything out and start from scratch. So look, I've got a little bit of headroom at the top, right? So what I'm going to do, throw it all away. But when I define my project area this next time, all I have to do is maybe just go like that, and that's going to give me all of the area that I need. So now I download the DEM, run Topaz, create the outlet, and delineate. All right, it's 1:49. We're out of time. So I'll put the assignment online, but we're going to practice this same stuff on Monday. And I think once, like if you practice it from today's class and going through it on Monday, I think the homework's going to probably take you about 30 minutes. So I think it'll be a really easy assignment. Don't get too worked up. I know you're busy with lots of things right now with senior design, and some of you are also in the 331 this semester. So this homework assignment won't be the heavy lifting, but we will get together on Monday and continue with WMS.